Um, all right, so this is the last day of numerical integration, and then there's only two more weeks of covering other stuff, and then it'll be Thanksgiving, which we'll all be very thankful to have a whole week off. Oh, that sounds too good to be true. And then after that, the only thing left to deal with is the final. So sometime, definitely before Thanksgiving, I will be putting out a practice final. The length of time you have is the same, because if a final occurs during our last class meeting, for some reason the university specified it that way. It's kind of weird, but so Thursday, December, I think it's the 5th, or yes, the 5th is when the final is, and the so the class period before that will be the review. So same kind of format, a certain number of regular problems on chapter 9, chapter 10, and the lightning round taken from the quizzes on those chapters. Okay. So we don't have any actual class activity or meeting of any kind during finals week, but finals week will be your last chance to get in any outstanding homework. So I need to lower the boom on commencement day, which is a Friday of finals week. So actually, let me put that down in writing here. Yes, I'm recording. Yeah, I was actually on top of things this time. Okay. December 12th. Okay. So, because final grades have to be entered in SOAR following Monday, December 16th. So, at some point, there simply isn't time to grade stuff. So, okay. It's not an invitation to wait till the 11th.
So only chapter 9 and 10?
Right. We're wrapping chapter 9 today, and then next couple weeks on chapter 10. There is one section of chapter 7 on interpolation that was not on the midterm. There may be a problem from that on the final, Hermite interpolation, but that's it.
On the lightning round or on either major question or lightning round?
Right, yeah. But yeah, it'll be mostly chapters 9 and 10. Okay. Okay.
Will it be 100 points similar to what we did with the midterm, or do you think it might be more questions overall?
Well, I'm not going to put. It'll be about the same number of questions, just because you have the same amount of time. So, was there another question up front? Okay. No. Okay. So.
Wait, it's actually 6:30 to 9:45, so more.
Really? Okay, I was not aware of that.
Wait, no. That's for night classes, not night
Stop it. Okay, so yeah, there's something about. Okay. Yeah. So Oh, okay. So that's
Oh wait, no, I think it is still 6:30 to 8. It's in the exam schedule.
yeah. So all the exams, no matter from all your classes, no matter what time they are, well, except for Saturday classes, which is unusual, but yeah, everything. Okay. Oh, that's weird. Okay, so these okay. Oh, okay. Exam time, 2 hours. Um, okay, but then okay. So then, if I look at 6:30, okay, that's Monday, Wednesday. That's the last day of class. Tuesday, Thursday, last day of class. Now, they're not clear about duration. Um, they might intend that it's also 2 hours, but since I wasn't aware of that until just now, I'm not going to deviate from what I said earlier. So, and I don't want to be here past 8, if at all possible. Um, so depending on the problems, last time it was 5 regular problems, 10 lightning round. It will be approximately that. I'm not going to rope myself in to say it's exactly that, but it's going to be not far from that. We'll just see what kind of problems I have. Okay. And that's 40% of a grade. Yeah, but it's not comprehensive. Okay. All right. Now, to finish off numerical integration, we're going to look at one more integration technique. It's called a Gauss or Gaussian quadrature. It's actually a personal favorite of mine. It plays a large role in my research program. So, I'm going to recall a term that I've mentioned before. The degree of accuracy of a quadrature rule is the highest degree of polynomial that can be integrated exactly by the rule. And what I can say specifically about degree, again reiterating here, for any n-node interpolatory quadrature rule, and by interpolatory I mean f of x approximated by interpolating polynomial, and then we just integrate the polynomial because it's easy. But degree is greater than or equal to n minus 1. And we've seen some cases where the degree is a little higher. All right, so can be higher. Simpson's rule has 3 nodes, and it's degree 3. So any cubic can be integrated exactly. Okay. Now, what we're going to look at tonight, is so we've seen how low the degree can get. What's the highest possible degree? So it turns out it's actually a question that's easily answered in terms of what is a top degree, but how do we achieve it is not so easy. So any quadrature rule has this form. If we have n nodes, so we have f evaluated nodes times the weights, and then we have some error. Okay. Now, we have a total of 2n parameters to set. We have n nodes, x1, x2, up to xn, and the n weights, w1 up to wn. Now, in interpolatory quadrature, the idea is that once we have the nodes, the weights are determined from there, because all we do is once we have the nodes, we form the Legendre polynomials for these nodes and integrate them from A to B, and those are the weights. But that says nothing about how we choose the nodes. Now, we have seen certain ways of choosing them, like equally spaced. That leads to the Newton-Cotes rules. But those are not effective when n is large. And then we have composite rules. But those do not have a very high degree of accuracy. So, but the point is, since we have 2n parameters, that gives us 2n degrees of freedom. So we want to take advantage of the flexibility that we have to maximize the degree of accuracy. And that leads me to what is called direct construction. Try to find the nodes and weights that satisfy the following. That if I apply this quadrature rule that's currently unknown to a monomial, so powers of x. Okay. So I'm taking my nodes and raising them to a j power, multiplying them by the weights. So what is this? This is an approximation of the integral from a to b of x to the j dx. And I'll let j go from start, since I have 2n degrees of freedom here, I can impose this for first 2n powers. J going from 0, 1, 2, up to 2n minus 1. So what we have here is a system of equations. 2n equations, because j is ranging over these 2n values. And we have 2n unknowns. N weights and nodes. Okay. So the solution of this system of 2n equations consists of the nodes and weights for a quadrature rule that has degree of accuracy 2n minus 1. So because we have 2n parameters, 2n degrees of freedom, then we can make these exact. 'Cause notice I have no error here. So the idea is this quadrature rule integrates these monomials exactly. So because that's all the flexibility I have, I can only impose 2n conditions. The maximum possible degree is 2n minus 1. But that's quite good, because before we only had assurance of degree being at least n minus 1. So now we're actually more than doubling that. Okay. Now, so you might think, okay, then however many nodes we have, we'll just solve this system. We'll have our nodes and weights, and we'll be done. Except there's one big problem. Like, if you have a system of certain number of unknowns and same number of equations unknown. Yeah, I can't talk. If you have a system of a certain number of equations and the same number of unknowns, everything same, how do you normally go about solving a system of equations like that? Yeah, Gaussian elimination, except you can't use that for just any old system of equation. What type of equation is that good for? Linear equations. Yeah, because that's a linear algebra technique. Is this a linear equation? No. because the nodes are among our unknowns and are raised to powers. So this is a nonlinear function of the unknowns, plus of the nodes and weights being multiplied together. Also makes it nonlinear. So the problem is this system of equations is nonlinear and therefore very difficult to solve, at least for the case of general n. It's not so bad for the case of, say, n equals 2. So 2 nodes, 2 weights, total of 4 unknowns. So I made that a homework problem. Okay. So for the case of n equals 2, you have equations for j equals 0, 1, 2, 3. So you'll set up this system of equations on a given interval, the integrals of 1, x, x squared, x cubed. You work those out exactly. And then these expressions for j equals 0, 1, 2, 3 must equal those values. So then in that case, it is possible to solve for the nodes and weights. But I wouldn't dream of assigning that for even n equals 3. It gets pretty obnoxious. Okay. All right. So this approach of setting up a system of equations and solving for the nodes and weights is called direct construction of these high degree accurate rules. So it's a simple method to describe in terms of a problem you're set up to solve, but actually solving it, no, we're not going there. So we're not going to look at this any further. We want to try a different approach to obtaining the proper nodes and weights. Okay. Right. And for that, use a rather unusual concept called orthogonal polynomials. So what does that mean? First, I need to bring up something that you learned about in Cal 3. Two vectors, u and v, are said to be orthogonal if their dot product is equal to 0. Okay. Now, dot product, in case you've forgotten, is so I'll assume that these vectors, for convenience, I'll assume they're in 3 space. So I'll make this a separate equation. And write out what the dot product is. So that would be u1 v1 plus u2 v2 plus u3 v3 equals 0. So what we do is u1, u2, u3, those are components of u, and similar for v. So you multiply corresponding components, and then you add them up, and we're supposed to get 0. So orthogonal, or synonymous with perpendicular when you're talking about Euclidean space. Okay, so those are orthogonal vectors. But what about orthogonal polynomials? What does that mean? So two functions, f of x, g of x, are said to be orthogonal if, I'll use this notation, the angle brackets indicating it's not we don't call it a dot product when it's functions. This is a inner product, and it's defined to be the integral from a to b of f of x, g of x, dx. Now I need to specify that what I just said is only valid if these are real valued functions. If they're complex, this definition of orthogonality is wrong, but we're not going to deal with that here because this is not a complex analysis class. So both of these operations, taking its dot product of vectors and evaluating this expression, so the expression fg is an inner product of f and g. So I say an inner product to indicate it is not unique. There are many different inner products I can define. I can choose the interval, any interval AB. I could put a weight function in here. That would be some positive function that is multiplying f and g. So any of those kind of things, expressions like this, are an inner product. The dot product is also a form of inner product. So inner products are very useful in many branches of mathematics, and they all have similar properties. They're all linear in each argument. If you take the inner product of a vector or a function with itself, that is like the magnitude squared of the object. And no matter what inner product we're talking about, if the inner product is always a number. So it's a mapping from two vectors, if you will, because f and g are members of a vector space, like a function space. So anytime we have some inner product of two vectors being equal to 0, we say they're orthogonal. Now, that doesn't have the same kind of geometric meaning that this one does, but we use the same term just for convenience. Okay, now so orthogonal polynomials are going to help us get with a better way of obtaining these high degree accurate quadrature rules than direct construction. All right. Now, okay, actually I'm going to put this on a new page. Okay. So on a given interval AB, there exists a sequence of orthogonal polynomials, which I'll refer to as, let me check my notation here. Okay. Q0 of x, Q1 of x, and so on, with these properties. So, first, Qj of x is of degree j. All right, so in other words, the first polynomial sequence, Q0, is a constant function. Q1 is a linear function. Q2 is a quadratic, and so on. Okay. Also, these polynomials, they're inner products, which are defined to be the integral over the interval in question, AB, of Qi times Qj is equal to the following. They're equal to, whoops, something went wrong here. Oh, okay. All right. Okay, we're equal to 1 if I is equal to j, or 0 if I is not equal to j.
It's both supposed to be Q of J in that first bracket to the left of the interval. One of them supposed to be an I.
Oh, yeah, the first one's supposed to be an I.
Okay.
Let me fix that. Okay, yeah, so inner product of Qi of Qj. 1 if the indices are equal, 0 if they're not. Okay. Now, I'm going to give a specific example here for the interval minus 1 to 1. Dang it. We have what are called the Legendre Polynomials. Lj of x defined by following. First polynomial in the sequence is 1. The second one, this linear function, is x. And then the rest of them, see if I have it written here. Oh. Nope, not in this section. They're actually described elsewhere in the book. Let me make this bigger. Okay. Okay, so there's a recurrence relation here. Okay, so we have Lj plus 1 of x is equal to okay. So we start off with these two being defined, and then each polynomial after that depends on the previous two. So we see that the previous one is multiplied by x to make it 1 degree higher, and then we subtract off this multiple of the one before that. Now, where else have we seen a situation where we have a polynomial that's defined in terms of the previous two? Like for family polynomials, each one depends on the previous two. Chebyshev polynomials. So those are also a family of orthogonal polynomials. Now, the Legendre polynomials, and they rate their own Wikipedia page, they do satisfy that if you take this inner product, the inner products of different ones are 0, but if you take the inner product of one of them with itself, generally not equal to 1. So what it means is they're not normalized to satisfy this same relationship, but you can scale them so that they would. It's just that then the definition would involve some square roots. It gets kind of cumbersome, so conventionally they're not defined that way. But this is a family of orthogonal polynomials on the interval minus 1 to 1. Now with Chebyshev polynomials, the polynomials which we've seen are orthogonal. Okay, and these I defined these previously as tk of x are orthogonal in this sense. So I take this inner product, but it's a different inner product than the one for Legendre, even though it's the same interval, minus 1 to 1. Because here we have a weight function 1 minus x squared to the minus 1/2 power, which, interesting enough, is undefined at the endpoints, but that doesn't actually present a problem here. Okay, so this inner product is equal to 0. In the case of j not equal to k. Okay. And there are many other families of orthogonal polynomials that are orthogonal on different intervals with respect to different weight functions. So the factor, so the factor 1 minus x squared 1/2 is an example of a weight function. Recall recently I was talking about the weighted mean value theorem for integrals, where you have a function that does not change sign on the interval of integration. So that's a requirement for a weight function. And in fact, if you substitute the Chebyshev polynomials in here, like their definition in terms of cosine and inverse cosine, you could make a substitution, like a u substitution, and you actually get integral of a cosine times a cosine, and that's how you show that it's equal to 0. Okay. All right. So these are some of the best known examples of orthogonal polynomials. But how does that help us with integration? Here's how. Okay. So let's suppose f of x is a polynomial of degree 2n minus 1 or less. So we want the following, that the integral of f to be equal to this quadrature rule. So in other words, normally an approximation, but not here. We want to be exact. But this is equal to an interpolating polynomial, the integral of an interpolating polynomial of degree n minus 1 or less. So more specifically, is the interpolating polynomial of f of x at the nodes x1 up to xn that at this point are still unknown. Okay. So we need to make sure that in approximating this integral by this integral, the error is 0. So let's examine the error. So the error will be equal to the integral of f of x minus p minus 1 of x dx. Now, this f of x is a polynomial of degree 2n minus 1 at most. This is a polynomial of degree n minus 1 at most. So the difference is also a polynomial of degree at most 2n minus 1. So what I'm going to do here for convenience is all functions I'm going to write here are polynomials. Just as I have everywhere else in these notes, I'm going to use a subscript to indicate degree. So here, this is, well, yeah, f is your integrand, degree 2n minus 1 or less, degree n minus 1, degree 2n minus 1. Okay. Now, what do we know about the error? Admittedly, not much, but what we do know is crucial. because f and this polynomial agree at the nodes. In other words, the error is equal to 0 at the nodes. So if you have a polynomial and you know some of the roots, and this polynomial has at most 2n minus 1 roots, but we know that these are roots, how does that help us write out the polynomial? Like if we know some of the roots, how does that help? How does that help me express what this polynomial is? Like, anytime you have a polynomial and you know the roots, what can you do to that polynomial? Sorry, what?
You can form the polynomial from the roots.
Set it equal to 0?
Yeah. What?
Set it equal to 0?
Oh, what? Yeah, you're factoring it. Yeah, so I can write this as in this form: x minus x1, x minus x2, and so on. Because these are all factors of this error. Because the error is equal to 0 at these points. Now, that's only degree n. The error is degree 2n minus 1. So I'm going to have something else here. I'm going to call it q. No, I can't call it q. I'll call it r. R n minus 1. Okay. So I'm able to partially factor this in terms of the roots that are known, where this difference is 0. And then I have this, polynomial of degree n minus 1. Why do I know that polynomial is of degree at most n minus 1?
I don't know. I feel like when we did interpolate,
This isn't really about the interpolation aspect, though. It's more of an algebra thing. Yeah, so here we have degree 2n minus 1. We subtract off n, because of the n known roots. This is what's left. All right. Now, suppose that we choose these nodes, x1, x2, up to xn. What's going on here? Oh, okay. xn. Still unknown at this point, but now I'm going to specify what they can be. To be the roots of qn of x, polynomial of degree n, that is orthogonal to q0, q1, up to qn minus 1. Because so it is, this polynomial is already specified up here to be orthogonal to all other polynomials in this sequence. And here I'm focusing on the ones of lower degree. And is therefore orthogonal to all polynomials of lesser degree. So then we have the following: qn of x is equal to these same linear factors. Times a constant, which I'll call beta n. Because those are the roots. I should mention one thing, it's not at all obvious, but one property of orthogonal polynomials, and this is proved in the book, in chapter 8, that a orthogonal polynomial degree n, when we know that such polynomial has at most n roots, except possibly for complex roots or repeated roots, but of orthogonal polynomials, in fact, we know, okay, so it can be proved that Qn has roots that are real, so no complex roots. They are distinct, so no repeated roots. And they lie in the interval AB under consideration. All right. So, the error that we have here is the following. So that would be fx dx minus the quadrature approximation. So that is equal to this integral right here, but what is that? That is going to be 1 over beta n times the inner product of Qn with this leftover polynomial, Rn minus 1. Okay. Just because of Qn having these linear factors. Now, Qn is of degree n. Rn minus 1 is of degree n minus 1. This polynomial is orthogonal to all polynomials of lesser degree. Therefore, the error is 0. So that is how we can maximize the degree of accuracy. So let me summarize. What we have is a Gauss Quadrature rule. Okay. And now I'll describe that. Okay. So the nodes x1, xn are the roots of a polynomial of degree n that is orthogonal to all polynomials of lesser degree. So the Legendre polynomials in the case of the interval minus 1 to 1 otherwise can be scaled and shifted. So if you're working on any other interval AB, the Legendre polynomial roots are still very helpful because you just do a linear mapping. Like you shift them to the center of your interval, so a plus b over 2, and then you multiply them by b minus a over 2. So really the transformation... Okay, let me... so it's a Legendre polynomial for this interval. Okay, let me put this on a new page. Okay, so equals xi plus a plus b over 2 times b minus a. Oh wait, actually, hold on. I need to do this in a different order. I actually have to do the scaling first. Okay, so this is for a case where xi is in minus 1 to 1. So like those would be the roots of a Legendre polynomial. And these nodes are in the interval AB. So those are the nodes you actually want for your integral. So it's easy enough to first scale, then shift to get to the right interval. Okay. Now, I just explained once you have these roots of a Legendre polynomial, how you get the nodes in AB. But how do you get to roots of the Legendre polynomial? Okay. Okay. So tables, wait, this should be part of a bulleted list, and I'm not sure why it's not. That's really strange. Sorry, something is really wrong with LaTeX, and it's driving me crazy. Oh, that's why. Okay. All right. So it turns out that tables of Gauss Quadrature nodes for the interval minus 1 to 1 and various values of n can easily be looked up. So in fact, I'll show you. I'll make this a little bigger. Okay. So here, for however many nodes you want, here are the nodes. So for each degree n, there are n nodes. So like here for degree 4, you have these nodes. You take both plus and minus. And these nodes also take plus or minus. And these are available up to degree, 5 in this Wikipedia page, but you can find in the higher degrees elsewhere. Otherwise, you could use the recurrence relation I gave for Legendre polynomials to form the Legendre polynomial you want, and then you can use MATLAB to compute its roots. Okay, but here we have exact expressions in these cases of lower degree. And there are also tables that list the nodes out to many decimal places. Out to machine precision, certainly. Okay, so that's how you get the nodes. Roots of Legendre polynomial, scale and shift as needed. Now what about the weights? The weights are given by, same as with interpolatory quadrature in general, so this is a formula for weight I. So you form the Legendre polynomials for the nodes, and you compute their integrals. Now, for low degree, again, not necessary, because formulas for weights are given right here. So here we have 4 nodes, here we have 4 weights. Now, if you look at the decimals of these weights. These are rather strange numbers, weird formulas, but can anyone tell me what all these numbers, just for the weights, forget the notes, look at the weights, what do they have in common? Not much, but what do they have in common?
The squares of numbers.
That's one thing, but what else?
The conjugate pairs.
Yeah, there's a certain symmetry to them.
Is the difference the same?
What? Okay. They're all positive. In fact, what's kind of weird about these weights is it can actually be shown that weights are defined to be the integrals of these Lagrange polynomials, but they're coincidentally equal to the integral of Lagrange polynomial squared. Now, it's definitely rare when the integral of a function is equal to the integral of its own square. That just doesn't happen in nature. But it does happen here, and it's because of these nodes coming from orthogonal polynomials that it works out that way. But showing it are equal to this makes it easier to see that the weights must be positive, because the integral of a positive function is going to be positive. And that's nice because we need to have positive weights, not positive nodes, we need to have positive weights for numerical stability. Now, Newton-Cotes rules, I mentioned, once they get up to a certain degree, you can't possibly get all positive weights anymore. But for Gauss Quadrature rules, no matter how many nodes you have, weights are always going to be positive. So what that means, the consequence is that as n goes to infinity, the Gauss Quadrature approximation of the integral converges to the exact value of the integral. Now you might think, well, duh. I mean, if you use infinitely many nodes, shouldn't that converge to the exact integral? And the fact is, it doesn't always. That does not happen with Newton-Cotes, for example. All right, but with Gauss Quadrature, it does. Okay, so tables of weights are also available. Posted online, published in certain books, things like that. Okay, and again, if on a general interval AB, you only need to scale the weights from tables, because the tables will be from -1 to 1. So you scale weights in tables by b minus a over 2. So you only do the scaling in that case, you don't have to do the shifting. All right. So Gauss Quadrature rules are among the most widely used quadrature rules for two reasons. One, they have this very high degree of accuracy, the highest degree possible, 2n minus 1, and because they're guaranteed to have positive weights. They do have a drawback, though, because, as you just saw, the formulas for the nodes, they're not very convenient. And once you get to high enough number of nodes, there may not be formulas. So it's not as convenient as equally spaced points. Also, the nodes are not progressive. So, for example, if we go back to the table, like here are the nodes for the case of n equal 2. But you do not see them among the nodes for any higher degree. So we're not progressive in that sense. N-node Gauss Quadrature rule is not easily extendable to rule with, say, n plus 1 nodes or 2n nodes or anything like that. Some people have gotten around that by developing similar quadrature rules that do build on earlier ones, but It's again not an easy thing to do. Okay, but yeah, but their accuracy and reliability makes them quite effective. And I'll give an example. Okay, so suppose we have this integral that I've shown you before. This Gaussian function from 0 to 1. How many nodes are needed to obtain 8 digits of accuracy using various methods? Okay. Well, first I will give you the composite trapezoidal rule. So about 2,500 nodes. So I mentioned that the composite trapezoidal rule is the most effective for periodic functions, but for a function like this, horribly inefficient if you want high accuracy. So let's not do that. Close relative composite Simpson's rule, due to its 4th order accuracy instead of 2nd order, it does much better. I think it's like around 33 or so. Turned out to be enough. So huge improvement. Until, look at Gauss Quadrature. 5. 5 nodes is enough. That is why people like Gauss Quadrature rules. You can get that much accuracy once you have the nodes and weights, with a whole lot more efficiency, because we're trying to reduce the number of function evaluations, and Gauss Quadrature is a great way to do that. Now, there are some integrals for which Gauss Quadrature may not be so effective, but on balance, it's the typical choice, one you often see implemented in mathematical software. Okay. Now, we'll say a little something about error analysis. So normally, we obtain the error in an interpolatory quadrature rule by noting the following, that the error which is defined to be the exact integral minus the quadrature rule approximation. But that is equal to the interpolation error. Where p n minus 1x is the, whoops, that should not be part of subscript, is the Legendre interpolating polynomial of degree n minus 1 of f of x at the nodes. And why this is helpful is as I've said, the error in the integral is the integral of the error, meaning that can replace f minus p n minus 1 with the error formula for polynomial interpolation and estimate the integral. So that's what's normally done. But this actually does not convey very accurately the error in a Gauss Quadrature rule, because that doesn't take into account that Gauss Quadrature rules have a higher degree of accuracy. So it turns out, and I won't go through the proof of this, it's in the text, but the result is this. For Gauss Quadrature, we have this. The error is equal to the integral of f minus not the Legendre polynomial, but the Hermite. Wait, that's 2n. Wait, 2n plus 2. Oh, wait, 2n minus 1. The Hermite interpolating polynomial. Okay. Oh. And something is okay. Where h 2n minus 1 x is the Hermite interpolating polynomial of fx that agrees with f and f prime at the nodes. Now, this is really strange because the construction of a Gauss Quadrature rule has nothing to do with a derivative of f. So how can it, since we haven't really been dealing with that, we just want an interpolating polynomial that agrees with f at the nodes, nothing about f prime. Why does this work out anyway? Here's why. This is because the terms in this interpolating polynomial that involve f prime at the nodes have integrals of 0 when the nodes are Gaussian. So if we choose the nodes to be ones for a Gauss Quadrature rule, yes, this interpolating polynomial has terms involving values of f and values of f prime. It's just that the terms involving f prime have integrals of 0, so we can ignore them. But we can still claim this. So what does that mean? So this means the error in Gauss Quadrature is the integral of the Hermite interpolation error. This is Theorem 751 that gives that Hermite interpolation error formula. So this is useful in a homework problem on the error. So, because the problem itself looks scary, even though it's a three-word problem statement, because the first word is prove and the second word is theorem. But you are given, the proof is actually not very involved because of the breadcrumbs that are given in the vicinity of a problem. So that I've reiterated one of them here. So it's not. This isn't real analysis. Put it that way. So, okay. But this is how the high degree of accuracy and the positive weights of Gauss Quadrature are properly taken into account for the error. In fact, I will show you the theorem right here. Okay, here it is. All right, so the exact integral is equal to the Gauss Quadrature approximation plus this error. Notice, as in the Hermite interpolation error, we have these factors squared. So what that means is, if we have certain functions for which we know that this derivative is always positive or always negative, which does happen for certain integrands of interest, then in fact we know the sign of the error. We can say conclusively that the error is positive or negative, meaning that the Gauss Quadrature approximation is known to be either a lower bound or upper bound of the exact value of the integral, depending on the sign of this derivative. And that information can be quite useful. There's some variations of Gauss Quadrature that I won't get into here, but it's in the optional subsection at the end. So they're called Gauss-Radau rules and Gauss-Lobato rules. So you can use these rules to get both an upper and lower bound on the exact integral. So in other words, you can bracket the exact answer, which is quite nice. Okay. So that is, well, I already mentioned what I want to say about other weight functions of, for example, Chebyshev polynomials. But it happens more often than you think that we actually need to evaluate integrals where we have some additional function w of x here, like that 1 minus x squared to the minus 1/2 for Chebyshev polynomials. So everything I've just said tonight applies when you have weight functions. All I've talked about here is just a special case where a weight function is equal to 1. Okay. Do we have any questions, including any homework questions? Oh, we do. Okay.
In 9.1,
Okay.
expression
1?
yes.
Okay.
So when you're doing the Taylor expansions, so you're, like in that example, you only had 2 different expansions. You had one for f(x0) plus h, and then you had another one for f of x of 0 plus 2h. But
Now there are 4
now
altogether.
there are 4. But how do you know, like when you have minus h and then minus 2h?
Yeah.
Maybe, I don't know, as I'm saying it out loud, it sounds kind of silly. Okay, I don't know. How do we know how that affects the minus h? Like, does that just negate all the h's in the
In other words, are you saying like
It's minus
the terms from f of x naught minus h negating the ones from f of x naught plus h?
So, like, I have f of x naught plus h. How do I, to have f of x naught minus h, do I just change all the h?
Oh, well, yeah. So one.
Is that easy?
Well, yeah, you can replace h with minus h throughout. Just be careful about the powers.
Right.
Like,
When you square, you can't post. When you power it's even.
yeah. So in other words, if you have minus h to the power,
Right.
yeah. So do it that way, and so it does not negate all the terms. It will negate
Right,
alternating
okay,
terms.
Yes. All right.
Yeah, okay.
That's my question.
Okay. So that does make it a little easier to carry out those. Okay. Other questions? Oh, do you have a question?
I guess I was it's on the question right after that. I kind of get where you're going.
This one?
Yeah, the 9.1.
Oh, wait. Oh, 914. Okay.
Phew. Excuse me.
Everything down to the end. I got some stuff over in the factorial, but it's not quite the in factorial I need.
Okay. I'm sorry. I'm having trouble hearing. But
Sorry. I don't know. I feel like it's kind of a spoiler, but
Oh, kind of a spoiler, or
Yeah,
um,
I think I figured out what you wanted. I just kind of stuck on the algorithm.
okay. Oh, okay. Maybe show me after class. Okay. Other questions? Okay, I won't keep everybody else here. If anyone still has questions, I will stick around.